Welcome everyone to the first edition of the CARINAS monthly colloquium series. I'm very glad on behalf of the first few members to welcome all of you. And we are delighted to have Annapurni Subramaniam as our first speaker. Before getting into the actual talk, I will briefly say a few words about the CARINAS forum. So this forum has Indian women working in astrophysics and related fields, particularly the ones who work in India and the first generation of Indian women who work abroad. Currently, we have actually 250 members, and out of these members, 87% are from the early career stage, which means that we are actually catering to women who are in the formative stages of their careers. And these are the stages where we start losing women due to the leaky pipeline. So among our initiatives, we have started off with a newsletter. And in this newsletter, we are planning to not just talk about the science that Indian women do, but also their experiences across time. For example, in the first edition, we actually captured 3 generations of women scientists. And do check out our newsletter. Our website is carinas.co.in. So our next initiative from this forum is this monthly colloquium series. And of course, we are delighted. Again, welcome everyone. And I will hand over the virtual mic to Sangskriti, who will now introduce the speaker.
It is our great pleasure to have Professor Annapurni Subramaniam for our inaugural edition of Colloquium series. She is the director of Indian Institute of Astrophysics, India, and she has been doing astronomy for last 3 decades or so, which is probably as old as some of us are. She was a PhD student in IIA, and then she became a postdoc and a research fellow at IIA, and eventually a professor and the director. So she is indeed the product of that institute. She is primarily a stellar astrophysicist. She has played a huge role in some of the India-led astronomy missions. One of them is AstroSat, which is India's first multi-wavelength space-based observatory. And she will be talking about that in today's talk. And she has also played some role in Aditya L1, which is India's first space-based solar observatory that is now flying towards the Lagrangian point. And she has also been in the editorial roles of some of the journals run by the Indian and Chinese astronomical societies. So without further ado, we will move on to her talk. And before the talk starts, I will just mention that all of you are welcome to write down your questions in the chat box. We will take all of them in the end of the talk. And also, before we leave, I would request everyone to turn on your video so that we can take a virtual picture. Thank you.
And okay. Before I move on to the results and talking about AstroSat and UVIT, etc., I just thought I'll give you a glimpse of what is Indian Institute of Astrophysics and what are the kind of things we do. So these are the various, we kind of are, as IIA, we are more than 50 years old, but the institute traces its origin to an observatory set up in Chennai, Madras in 1790s. And then the observatory moved to Kodaikanal in 1899. And the Kodaikanal Observatory is still functional, and it is now functioning as a field station. But in 1971, the Kodaikanal Observatory became an autonomous body under the name Indian Institute of Astrophysics. And from then it moved to Bangalore as this where I'm sitting now as the headquarters. But then over a time scale, it developed many other field stations as well. And now we have, after that, we set up Kavalur for nighttime observations, which is in the southern Tamil Nadu region. We also have Gauribidanur Radio Telescope Observatory, which is in Karnataka. And we also have a campus near Bangalore at about 35 kilometers away from here. which acts as an extended campus where we have the Space Science Laboratory as well as the facility for the 30-meter telescope project. And we have also field stations up in Hanle in the Ladakh region, one at Leh and one at Hanle and Merak. And we are also setting up a planetarium in Mysore under the name Cosmos. So you can see a highly distributed campuses of this institute. And we do both nighttime and daytime astronomy, and researchers use the data from these observatories as well as from other observatories to carry out, practically cover all topics of astronomy and astrophysics. We have a large group on solar physics, and then a large group on stellar and galactic physics and cosmology, and we also have a theory group. And we also have a large number of engineers who support all these activities. On the space front, we have two instruments. One is UV-80 onboard AstroSat, and which has completed 8 years of its operation. And I delivered this payload in collaboration with other organizations. And I host the Payload Operations Center for UV-80, which is seen as two yellow tubes on this. We also have delivered the VELC, which is sitting on top of this in the bus, ISRO bus, the coronagraph, which is right now getting ready for the pre-commissioning phase, and will start operations very soon, as soon as the spacecraft reaches the L1 point. And so these are the two major space payloads delivered by IA. And I also host the Coordination Center for the India 30-meter telescope project, and India is a partner at the level of 10%, and of the 10%, 70% have to be delivered in kind. So the team at IA, the ITCC, coordinates with various industries for developing. Major delivery from India include about 80 mirror segments polished. There's 1.5 segment size, and all the support system for 492 segments and spares, coating for the mirrors M1, M2, and M3, and some of the software and contribution to the science instruments. So this is a kind of a major delivery from India, and that is coordinated at IA as well. So I've been the director of this place for the last 4 years. And prior to that, I actually did my PhD here. And after that PhD, I took a break for a year when my daughter was born, and then maybe a year and a half. And then I came back as a visiting fellow for about 2 years. And then I joined as a faculty as one of the very low entry-level scientists. And then I kind of climbed up the ladder, and then became the director of this institute. So I'm basically the product of this institute, and whatever research I have done so far is actually done out of this institute itself. So that's just about me. And of course, the kind of things you need, what I need to tell you is that you have to take things as and when it comes, and you have to, you should never have a kind of a option of quitting on the table at all. So you need to figure out a way how to take it forward, and never should have a quit as an option on board when you discuss on the table when you discuss options. So you probably can go slow, but don't talk about quitting. So that's what I think I have learned over the time scale. So going forward with my, okay, one more slide on the pictures of various instruments and observatories I was talking about. So this is the VLC before delivery. This is the Hanle. This is a high altitude desert. So this is a 2-meter telescope, and this is a 70-centimeter telescope. And both are operated out of Bangalore. So it's a remotely, this is remotely operated, but this is robotic. Basically, you upload all the observations to be taken that night, and it does a robotic observation, 70 centimeter. This is a Hosakote facility for fabrication, mirror fabrication. These three are from Kavlur, pictures of Kavlur Observatory. There's a Gauri Bidanur dipole array, and the Kodaikanal tunnel telescope, and the AstroSat before launch. So coming to the AstroSat and UVIT details, this is the UVIT shown here as 2 tubes as part of the multi-wavelength observatory. AstroSat is a multi-wavelength observatory which covers from hard X-rays up to visual. And you can see the Caesar TI, LAX, PZ, SXT, etc. These are the X-ray telescopes. The SSM is the scanning, sky scanning telescope. So this scans the sky for bursts. And in the UVIT, there are 3 channels, far UV, near UV, and visual, and it operates in the photon counting mode. It's an MCP-based detector. And so these are the specifications. And in the specifications, you should see, if you're comparing UV with Galax, these are the spatial resolution, particularly the spatial resolution is extremely good. Though Galax has a better effective area and a larger field of view, the resolution of 5 arcsecond actually gets quite poor when you consider crowded population or in the galaxy stuff, regions of galaxies, etc. So the resolution shown here is 1.8 arcsecond. There was the design specification, but in reality we got much less than that. So up to 1.5 to 1.3 it can go, because it's a photon counting mode and you can correct for it and then get as much as possible. The current situation is the far UV channel is working well. Near UV channel got issues after a couple of years, and so it is not functional. Far UV and visual are functioning very well. And so this is the payload. So the design and development is done here with collaboration with other institutions. The design from here, and then fabrication done from other organizations, the mirror from LEOS, etc. And then it is integrated in our space science lab, which was specifically built for this facility and maintained. And so this is the individual payloads. You can see this is the far UV and this is the near UV. Near UV has two detectors, one visual and the other near UV. Far UV, I mean, why you can ask why you want 2 telescopes? It's a twin telescope. Why can't you put it in one telescope? The issue is the following: the UV, if you use, there are multiple issues with respect to cleanliness. Far UV is very tricky, particularly because the molecular absorption and contamination controls are extremely stringent. Also, when you collect far UV photons, it's because of contamination and path length, it moves as and when it encounters an air molecule or a molecule, the far UV photon gets absorbed. So the entire efficiency comes down, and you cannot transmit through any other material. It gets completely absorbed. So you have to use only reflective optics. Only the absorption is through a crystalline filter and then the detector. So if you want to use only reflective optics, there will be only one imaging focus available. So that is the reason why it is split. In Galax, actually, for far UV goes straight and NUV gets reflected. Here, both far UV and near UV are completely straight channels, and the visual gets reflected, and we split it into 2 telescopes here. And we also have developed handling mechanisms and testing things, because since space instruments are very different compared to the ground-based instruments, because you need to design it to make sure that it survives the launch and etc. And the space environment. So all the and tested sufficiently to make sure that it works in space. So these are the equipments, and handling equipments are completely new. The beam to test, etc., has to be developed and tested. So this is all done in the Space Sciences Laboratory in the extended campus of IAA. So these are the things in progress shown here. Again, a lot of protocols, a lot of we have to devise a lot of things in-house to get everything ready, because eventually you will be delivering only the telescope and the components, but the testing equipments, baking, all the handling thing, all the things required in the laboratory, we need to design and get it and procure and set it up and also maintain. So that's the story. And this is the UVIT on vibration before it's a shaker, and this is the baker. So this is all done, and then the transport, and you have to make sure that at every time the instrument is safe, secure, and contamination free and launched. So you can also see that during even the checkout phase, the final phase before the integration onto the spacecraft, etc., the UVIT is purged with dry nitrogen, so that even if there is contamination, it gets kind of blown out of the system. So I was a calibration scientist on it. So I actually, you can ask what do you do as a calibration scientist? So my responsibility was to get the individual component level calibrations and integrate it and predict its performance. And so that you can, when you put the telescope on orbit, you can actually come up with observation plan for calibration, and also test it and calibrate the instrument and predict how much, or predict, but you have to actually match the observed flux with the predicted flux and see how much it is deviating. So along with the prediction, I also manage the performance verification phase, which is the first 6 months for UVIT observations, and carried out all the data, proposals, capture, analysis, and completed the calibration. So these are the filters available, and then these are the, after calibration, the effective areas, which would mean that you can see that the far UV is very less because the absorbency is very, efficiency is very less. So it acts like a 10 centimeter square telescope. On the other hand, the NUV is much larger. It acts like a 50 centimeter square telescope. So these are the various filters available. So NUV is not functional, but the first 2 years data, whatever is observed, is already public. So if you want to use any of them, you're welcome to do so. I'm sorry. Far UV is functional, near UV, visual is also functional, but far UV is the science instrument. Visual is not science instrument because the far UV is a photon counting mode observation, and visual is an integration mode because the same detectors are used. And if you use the photon counting mode, what would happen is a photon hits the MCP plate and it produces a shower of electrons. And on board, what is done is you basically get the centroid of that each shower and the time. So you get the photon time and the centroid. And then each frame, each readout will have this information of the locations along with the time tag. And then you get all this data down and create an image. That's what happens in far UV. But visual, there are too many photons for any object. So you can't operate in a photon counting mode where too many showers will be there. So it is done in an integration mode where, in fact, not the photons, but the showers are collected as an integration mode, which would actually defy you from generating a centroid list. Hence, the resolution or the PSF is much larger, and which is also because you're not collecting the photons and the showers. And the showers, we do not know for each shower how many electrons are produced. You can't calibrate it. So it's not scientific use, but visual always helps in actually identifying the field and some drift corrections, etc. So what do? I mean, basically, I have studied star clusters in the open clusters, globular clusters, and also OB associations. But the UVIT is, the OB stars in the galaxy are too bright. I should also point out that the sensitivity is such that the too many photons coming into the detector due to OB stars can damage the detector. So we cannot point to the galactic plane because there are too many bright stars. And I also should tell you that there are certain things which you need to satisfy for the observing proposal to be accepted in UVIT, where it should be looking at place where it is not having any too many bright sources, and the definition of bright source is also given there. You need to actually calculate and predict the number of photons from a particular object and see whether it will trigger the bright object detection system. So the earlier algorithm and the framework how to do that I had developed, but now it is modified and improved, etc. So initial phases, it was the one which I developed was used in here. But I did study the star clusters in the external galaxies, which you see as a integrated source. So I've studied star formation in galaxies, but I'm not going to cover those aspects now, and I'm not continuing to work on such topics now. But I mean, let me put it this way: I'm supporting the activities and I'm supporting the science, and I probably am co-authors of many papers which deal with star formation in various types of galaxies, but I'm not leading those studies. So I have led studies on open clusters and globular clusters, and there are a lot of theses which have come out of these two, and maybe in this Deepti I saw in this meeting, so she used these extensively, and I'll be showing a couple of the results as well. So what do I study in open clusters? Open clusters are groups of stars which are formed. Cluster is a kind of a group of stars which are formed at the same time from the same molecular cloud. The only thing difference is the mass between stars are different. And because of that, as and when these stellar groups in age, the higher mass stars keep evolving. So they create a pattern of their evolution. So we call that the turn-off, and the red giant branch, etc., can be seen in older clusters. So if you look at it, take a snapshot of this plot of their luminosity versus temperature, or in the observational plane, magnitude versus color, then you can actually trace a evolution of stellar evolution. And this is a picture of clusters of various ages shown here, and the older cluster showing the M67 showing the subgiant branch, red giant branch, etc. On the other hand, HN Kuiper has this gap, Earth spring, the gap, as well as only the giants are seen, just the turn off and the gap. So these things, this is basically coming from the single star evolution. But if you look at the Kalamanchy diagram of clusters, you do see this extended blue branch, as you can see on the right side. So the stars which are defying the turn off and going to the red giant branch are called blue stragglers. So it used to be, quite a puzzle earlier, saying that why these are crazy systems, why they are defying the stellar evolution, in fact. So we now know that they have probably, the members, the kinematic members of the cluster, who have actually defied the stellar evolution is because they have gained mass. The question is how they gain mass, etc. So my aim is to detect them, identify them, find out, probably throw some light on the formation mechanism of these blue stragglers, and also diversity among these gap stars. There are some stars which are found between the main sequence and the white dwarf sequence, which happens to fall like a vertical line with a high temperature, low luminosity side. So basically to look at these kind of objects in open clusters, because UV is the only way you can detect them and find them, trace them. So in the case of globular clusters, there are hot stars which are coming onto the, again, the blue straggler case, but we also have a lot of hot stars which are helium burning, core helium burning stars, and they have a range, and they actually can be found in the cores of globular clusters. So they have there are a lot of evolutionary questions which we don't understand about them. So the focus for globular clusters will be stars which are hotter than about 8,000, and understanding their evolution, which are co-helium burning or core hydrogen burning. So as you can see from the diagram here, the hotter stars emit more in the UV, and then if you see in the UV, the bulk of the red stars shown here, they actually do not emit much of a flux at all. So if you can see the flux at the blue end, the 4,000 has very little flux. On the other hand, the 6,000 has much larger flux. So the in the left diagram, the stars which are shown as red actually become very dim. So you can actually pinpoint and pick out the hotter stars from and you won't have any crowding because of the cooler stars. So this is a diagram which is very nicely done by Sneha. She also completed a PhD with me and using UVIT data. So this is put forward by her for an easy understanding. So this is the blue straggler stars. Earlier used to be thought as non-members because one can't defy stellar evolution, but then one now sees them as kinematic members, as well as they are very much in the cores of globular clusters. Now, the only reason why they can still continue to burn hydrogen in the core is because there's some extra fuel. And where does the extra fuel come from? You can have it as a mass transfer in binaries as a vampire star, or you can have in collision, which is possible in dense systems like the globular clusters, or hierarchical triple systems, where 3 stars and then the inner binary gets tighter and kind of spiraling and merging, basically. So we do not understand collision, of course, happens in globular clusters, and the top one, the binary mass transfer, is probably popular in open clusters, and the third one might happen in more systems with larger number but not dense enough. But these are kind of theoretical. I mean, you can expect them, but you don't know what exactly is happening there. So one of the ideas to figure out what are the formation channels and what are the environments in which formation channels can take place. So if by intuition you could say that the collisions are most important or only thing happening in globular clusters because the cross-section for collision is very small and they collide most of the time. So it's a collisional system. So you can we rule out the mass transfer scenario? And do we see hierarchical triple systems in open clusters? So these are open questions. Unless and until you detect them and find the formation channel, you can't say which way it is formed. So UV is a pathway to detect the hotter companion, presence or absence of hotter companion. So UV is used in that study. So the channels which we are looking at is if it is a merger product, then you will get only a single star. And if it is a binary product, you will see a white dwarf binary companion. But you may also see, so the question what we also are asking is that, are we looking at the normal white dwarfs or different types of white dwarfs? So the binary mass transfer can happen at any time. So if you look at a mass transfer happening at when the star becomes really big post red giant branch, so the core of the star left behind will be kind of a white dwarf. Now, what happens if the mass transfer starts very early in phase? So what is the kind of output you get? So though we tentatively say that mass transfer products by it's a product of a mass transfer, the details need to be found out for two reasons. One, when did the mass transfer take place? And because of that, what is the end product? And point number two, because of mass transfer, what is the chemistry which has changed, altered on the surface of these stars? So do we see any chemical, apart from the mass rejuvenation, do we see any chemical rejuvenation in these stars? And so what is the outcome of different types of mass transfer? So though it is not understood so far. And I also wanted to mention that we do have come across systems like low mass white dwarf recently. In general, if the single star evolves, you will say that the mass at which the white dwarf is formed is about 0.4. And the single star which evolves, which is as old as the universe, which evolves, will produce a white dwarf of 0.4. If you want to have a white dwarf due to single star evolution, the universe has to be much older than that. But we do see white dwarfs which are about 0.2, 0.3 solar mass, etc. Now they cannot be produced by single star evolution. The only way it can be produced is by I'll come to it. It is basically when the cores are stripped much earlier before it allowing it to evolve. So I'll come to that. So the question is that, so whether what are the different channels and what is the kind of mass transfer we get, we can find in the blue stragglers, and is it just a mass transfer which is the same type of mass, or it's chemically rejuvenated as well? And what are the outputs of this, the remnants of these mass transfer events? So these are the kind of questions we were answering. Initially, we got a few. We went on to observe the.
Didn't get that.
This one.
Could you try again? Get that. Could you?
Sorry, my Siri got down for some reason. So initially what happened was, as I mentioned, the bright object detection was so severe and the constraints for that was severe. Basically, the fear was that the detector should not get burnt out quite fast. So the objects which were bright were kind of not allowed for observation. So we had to use only globular clusters which were actually much less in brightness, and also not so much so many UV stars in the center. And so this was 1851 was the first observation as part of the performance verification phase, which I had proposed and got the observations done and also completed the analysis. And so this so Sneha is very much part of it. And we realized that the Galaxy UV, if you compare the Galaxy UV and the UVIT data, you can see very nice resolution difference, and you can actually see most of the stars in the core. And the observation also allowed us to kind of get some time variability of our UV stars. So we have not completed the data, analysis of probable R-related stars, but it's possible, because if you look at R-related stars, which are actually pulsating stars, they pulsate because of mechanism within, and it's a shock-driven pulsation. So far UV can penetrate into the inner photons, which are high-energy photons coming from the inner part, and it's closer to the shock surface. So the pulse you get for far UV will be a few magnitudes compared to the infrared, which will be about less than a magnitude of a few decimal places. I mean, I think a few tenths, 0.5 maybe, yeah. But you can actually get a shock of about 3 magnitudes in far UV. So we can actually get the details of the flux, but that's possible still, but we have not yet completed we have studied in other clusters also, but this is what it came out of the study. And so this clearly proved that we can do a very good analysis of or study of hot stars and clusters, but we were short of models the very first time itself. And it's important that you get data, but then without models, we can't explain what we have observed. So models were scanty, so we could not do much of a science with it. The second one was Sneha's, this is also Sneha's study, and this is from NGC 288. This is the first picture I showed you. And what we realized is
Annapurni,
yeah.
There are already some questions. So would you want to take some of these questions at this stage?
I will lose track of what I'm saying.
Okay. Let's wait for the end.
Okay. I'll just take a look at it and see whether it is worth answering now. But I get digress. That's the only problem.
No, I can do that for you. But we can wait until the end. It's fine.
Yeah. Yeah. Sorry. So the horizontal branch stars, which I was mentioning, which is basically not horizontal anymore in the UV. If you want me to go back and explain that, so this basically is a horizontal branch. So this mostly the luminosity is constant, but the temperature changes. These are cohelium burning stars, and the helium core mass is same. So the luminosity is same, but the temperature is large variation of temperature you see from about 5,000 to actually it goes up to about 30,000 is because of the envelope thing. And we also know that the way in which the stars get distributed on this is depending on the metallicity or the number of ions which can absorb the flux in the envelope. Now, we also know that clusters with the same metallicity can have different types of horizontal branch. But what I wanted to tell you is that the horizontal branch is named as horizontal because it is observed as horizontal in optical. It's an optical-based naming. But if you go to UV, the temperature becomes more sensitive, and since there is a steep gradient in temperature, the entire the magnitude axis becomes slanting. So there is a slope there, and you get the axis like this, and it should be, since there is an increasing temperature, you expect the horizontal branch to be completely slanting and going up. But we see in this cluster a changeover and a kind of become horizontal after a particular temperature. We also noticed that spectroscopy from these 3 stars, which are shown in red, also indicate larger elemental abundance for these stars. So we kind of started suspecting that there is a diffusion which actually pushes some of these ions up to the atmosphere, can actually act as absorbance and reducing the far UV flux. And that starts operating at about 12,000. So this is a clear indication of at what temperature this diffusion starts acting. And initial models had not incorporated enough diffusion to fit these, but later on the model started incorporating, and now we are able to fit it. So early observations and early papers, we did not get good fits with the models because models were not available. The other one is the one with NGC 546s, which is an outside blue straggler, where we got a companion. And it is also known that this blue straggler is actually part of the cluster because this is a radial velocity. So sometimes we do get sources which are very bright in UV, but they're background galaxies. So you have to separate it. So this is done here, and this is the temperature, and the white dwarf is detected here. But we don't know whether it's a mass transfer product, but then we can say that the binary systems do exist in the outskirts of globular clusters. So this is the first one of the first evidences that outer regions of globular clusters can act as a very sparse field, and the binary system can be maintained. And we again found another a star where the blue straggler combined into an extremely EHB star, extreme horizontal branch star, which would mean that there's a low luminosity EHB, and there are also a number of places where you see the EHB, the extreme horizontal branch, to be low luminous. Now, we don't know the reason for the low luminosity, but suggested that it could be in binary systems. So this is one possible boundary mass transfer process, because its companion is a blue straggler. So this is an indication that the low luminosity EHBs could be products of binaries. And this is Deepti's work. So these were the kind of survey work which I had carried out due to some observations possible with some of the clusters. But then based on this result, we started the survey. So these are the pre-survey globular cluster results. Now, this is a dense cluster, and it was a very difficult object to work with because of huge crowding you can see here. And we cross-matched this data with the HST data. And you can see the HST data covers only inside. The outside, we did not have HST data, but ground data we used. And the aim of this thing is to look at the evolution of stars beyond the horizontal branch. And you can see a number of them evolving away from the horizontal branch in this diagram. And we didn't detect any of them going in this, the red part, because it's much cooler and we can't detect. But you can see them, many of them going in these stars. And these evolutionary stars are called HB Mang stars. And we also have a couple of very hot stars which are evolving off. So the issue is here, these stars are actually in the inner regions of these clusters. And it was earlier very difficult to get an idea of either the number or the evolutionary path they take. So UVIT did help us identify some of them. You can still see the two stars actually are beyond the model grid available, and we are not able to fit these. So models are still has to be fine-tuned to figure out what kind of an evolutionary sequence the star number 23 and 24 would be going through. So initially we had several surprises with respect to their location, the CMD as well. The other cluster, which is the part of Sharmila Rani's thesis, is NGC 1261. Here, this cluster is known for about two branches of blue straggler stars. One is a collisional product. The other is supposedly a mass transfer product. This is a co-collapse cluster. But we do not see any kind of sequence when you change the magnitude in the magnitude axis, like which filter you want to take. So it is important to find out that it is probably not working in the UV filters. And we also checked whether they are of the same kind, but they are not. So the work is still in progress. But the important aspect of this work is that in near UV as well, this is one of the clusters where you have near UV data. The model is not fitting the data. Data is actually going fainter here, but the model is actually brighter. So still fine-tuning is needed because some opacity is unaccounted. This is another study on 2298 where we get again more stars which are going through this Mang phase. But by this time we had more models on early, late flasher and when exactly the helium flash takes place. So this is compared here. And we probably think that these kind of scenarios can create stars of various types. But again, these stars are newly discovered, and the hot stars are newly discovered in this cluster. So with this with this background, we proposed for a legacy survey where you can actually collect the important thing which we learned was that UV data alone cannot give us information. It has to be combined with optical and probably with the enough resolution so that you can identify them. So it is important to have HST coverage. So these legacy survey, we took everything from the Hugs catalog, and they have near UV, so we can actually cross match and get the far UV part of it. And far UV included, can be an extended Hugs catalog with the far UV information as well. So this was proposed as a legacy survey, and we have studied 11 clusters, and we have about 24 observed. Many of them are still available, yet to be analyzed. And most of the data are public, and some of the catalogs are also public. So anyone interested can use it for your own studies. So this is the map the kind of observation and the image from far UV. And you can see that some clusters are very dense, some clusters are sparse. If there's very dense, the central region we cannot analyze, that is left behind. But whatever is possible is analyzed. And this is the master CMD from the paper 1 of the globules. And this is the the previous Shavan et al. Paper, where you can see a blob here. The two issues, this is the x-axis is the UV, far UV minus near UV. On the other hand, here the magnitude axis is far UV. On the other hand, the upper plots show magnitude in far UV, but the color is far UV minus optical. And when Shavan et al. Did the work, the membership was not available. So all sorts of stars are here, whatever they detected. Here, this is membership based. And one major difference is that this blob is resolved here. We have got them, but then the same the stretch of horizontal branch stars you can see, and then the Manx stars are here, post HB stars. But the very bright ones, we have not detected them. Probably they're saturated, or probably they are non-members. So we don't know that. But this is the combined diagram, and you can see a very nice horizontal branch with less scatter in the cooler part, redder part, but quite a bit of scatter in the hotter part. And the blue straggler sequence and the white dwarf sequence. So moving on, we also studied this is part of Ranjan's work. This is the difference in just like I said, that the horizontal branch can be like these two clusters, M3 and M13 are called the second parameter problem, when you have two different morphology for the horizontal branch, even though they have the same metallicity, which would mean that the atmosphere, the color of the horizontal branch is not only dependent on the the metallicity of the thing, with metallic ions present, something else, because the horizontal branch of the top picture, which is M13, should be same as M3, but M3 has cooler stars, but M3 has hotter stars. So something, M13 has hotter stars. So something else is working here, and probably this is because of the helium, the distribution, the delta He, which is present in the cluster. But we do not know whether it is because of primordial or it is because of the evolution. You can also see that the hot stars produce a large scatter in the luminosity as such. And we do not understand because the luminosity is fainter than the models can produce. And this is a point of worry, because stars brighter than that is because of evolution. The lower than that, we do not understand why. So this is a still burning problem, and we are not able to find an answer for it convincingly. We see more such problem in the omega San work, which is led by Deepti. And we can see this much of omega San, and the central region is from HST. And in fact, omega San is much larger than this itself. So what we see in here is that the horizontal branch actually kinds of comes down much fainter and a lot of scatter, and the much more than what we saw in M13. And so this is real, and the difference in magnitude is about more than half a magnitude. And we went back and checked all the calibrations, etc. It is not due to anything. So this is again still an unsolved problem. We do not know what is happening to decrease the far UV magnitude as we go to the bluer end of the horizontal branch. And now we have proposed for a larger coverage of the omega San, because omega San, we have been able to cover only the central region. The entire omega San survey itself is proposed. Probably we'll get more information about stars in the outer region of this cluster as well. So going to another area of blue stragglers and blue lurkers, you've done both in the cluster of the globular cluster as well as open cluster. The idea is that, as I mentioned, the star which is like B here, which is actually mass has been transferred and it is rejuvenated. And the star which transferred the mass ends up as a white dwarf or whatever, a remnant. But if the star is close to the main sequence turn off, it kinds of moves away and you can actually detect them. What if the donor, when it moves away, the accretor stays on the main sequence itself? Like if it is fairly well below the main sequence, turn off, then it'll move up closer to the turn off, but it will not become a blue straggler immediately. You may call it as a potential future blue straggler, but recently it has been named as blue lurker. So we also call them as a blue lurker. The idea is that the location of the star is not above the turn off, but well within the main sequence of the cluster itself. Now, this is we found such things in the main sequence. Sorry, in 67. But before going to that, I wanted to say that in the open cluster, this is the first study done on M67. Why M67? It is the nearest. It's one of the nearby clusters as old as the sun, and a lot of binaries and a lot of blue stragglers. And so far, people have thought that all the blue stragglers are because of mergers, or, it's a single entity. There are no mass transfer blue stragglers formed in this cluster, but we could identify one. You can see the 3 SEDs here along with the IUE spectrum itself. The photometric data points and the spectrum and the model fit very well for the first 2 ones. The bottom one, you can see that the spectrum falls down quite rapidly, but there's still a lot of excess flux in the photometry as well as spectrum obtained from IUE in the blue part. And when we fit it, we get a white dwarf of mass 0.2. So what is 0.2 white dwarf? So this was what I was mentioning earlier. If a star evolves, it becomes a red giant towards the tip and then comes back onto the helium core burning, then the mass has to be 0.4. You can't produce or more than that. So 0.18 would mean that it is stripped core. Basically, when the sun evolves from the main sequence and immediately it becomes a subgiant branch, you can strip the core, and the core mass when the star evolves from the main sequence will be 0.18. So the stripping happens extremely immediately after it just becomes a little bigger. And how do you confirm that this is the case? It is, we recently looked at the variability of this particular star in TESS and K2. And this is, in fact, it's a very interesting thing that the star is a delta Scuti pulsator. And it pulsates. So it has accreted mass, but the matter has settled and it pulsates like a normal pulsating star, which would mean that it is stabilized. And we have checked that the frequencies of the delta Scuti oscillation shown here is same as any other delta Scuti star. But it shows this kind of a profile, and this is a kind of a very asymmetric profile. This is not because of eclipsing. It's actually it is a variation due to the deformation of the star. So this system is slightly deformed. We have modeled it with Phoebe, but the estimations we get from Phoebe estimations and the light curve is identical to what we get from this particular estimation, confirming that this is a low mass white dwarf stripped core, basically. We have studied a lot of clusters under the UVOX, which is basically the open cluster study, and the kind of objects we have studied are blue stragglers, yellow stragglers, horizontal branch stars, subdwarfs, white dwarfs, and planetary nebulae. And this work led by Sharmila is actually a very interesting case of a star cluster with a planetary nebula. Now, if you can see, all the low mass stars are evolving in the open clusters, older open clusters, right? So we should be able to see a lot of planetary nebulae in open clusters, in fact, but we don't. And this is one of the, I think, 2 or 3 cases where it, at least in the vicinity, we can see it. So we can see the UV-80 image with a nice nebula around the star, which is basically the planetary nebula. In fact, 2818 is given as a name for both the planetary nebula and the cluster. And in this work, we have studied the properties of this planetary nebula and the properties of the cluster. And we find that the planetary nebula can be a member of this cluster. So this is probably one of the cases where the star evolved from here. And so you can actually see the evolutionary path, and we have placed it in the luminosity and temperature because we can account for all the flux coming out of it. And it's possible to be a member of this cluster. And more analysis with respect to the planetary nebula is in progress. Now, you can also see in this work, there are a lot of stars which are between the path of the white dwarf and the main sequence. And this is actually a gap area where standard stellar revolution or single star revolution cannot produce any output. The single star revolution has to put output here only, not inside. Now, we do see many such cases, and the stars which are shown here, 1 and 2 as binaries of this yellow stragglers are actually sitting here. What we have shown here in purple and green are the field low mass white dwarfs and the subdwarfs A type. Now, we did not know, subdwarf, the low mass white dwarfs are found as in binary companions, but subdwarfs A are not in general. So we kind of believe that this area is occupied by strip core products, and it is indeed required that the mass transfer has happened. So these are the remnants of the mass transfer systems where the core is this is the remnant core, not the actual. It has not gone through the full evolution like the single star. So going further, we have another one, the 10th work from this series. There are many work which I'm not covering in this particular talk because there are too many of them. But in summarizing, what we are saying is that we do see a lot of them starting from the low luminosity EHBs to SDBs to low mass white dwarfs to SDAs, etc. all fall in this region. And whenever we identify the hot companion to a blue straggler or a yellow straggler, they fall in this region, which would mean that these are all strip cores. So though we call them with various nomenclature, they're all belonging to same category of the strip cores, but then the difference is that when the stripping of the core has happened, that is different. So you strip the core earlier, you end up as a low mass. You strip the core later, you end up as a subdwarf B, etc. So I think we'll be working on something like a consolidation of all this work to figure out and propose what kind of a scenario, mass transfer scenario, is actually producing these kind of stars. So do we see these kind of stars in globular clusters? Yes. So NGC 362, which is a recently globular cluster, we have actually able to trace these two things, and this work is led by Arvind from Aries. And you can see that we do see blue stragglers of two sequences, red and blue, and the red ones are the binary BSs. We get the binary hot companion now sitting here. We are all low mass. So we do see the low mass binaries in globular clusters as well. And we also have seen some blue lurkers, which are actually sitting on the main sequence. And we have seen blue lurkers even in NGC here. Many of the NGC 6791, many of them are here. So maybe the open clusters and globular clusters also have these blue lurkers. And another one which is submitted after revision is the 11th one in the study. We have again blue stragglers and having all series of mass right from 0.2 to about about 1 solar mass white dwarf. So massive white dwarfs are also here. And for instance, we are also getting the independent estimations of them from test light curves. So as I mentioned earlier, the light curves are kind of not symmetric, basically because of the distortion in the more massive star.
To get that, could you try?
So I'm just summarizing the talk. So the highlights from the study on the open cluster study is there's a significant number of case A, case B mass transfer products leading to the strip cores. And there's a lot of closed binaries that are present in open clusters, and they're going through stable mass transfer, resulting in a lot of strip cores. And this is very difficult to model. So models have not been able to come up with how much is really possible. But a number of, the end products of missing binary things are already here. The second thing is the blue lurkers. The mass transfer do happen in main sequence binaries, leading to jump of main sequence stars. So many of the main sequence stars we see could have been already acquired mass. And in these cases, when the mass transfer happens early in the evolution, the matter transfer is not chemically enriched. So the chemical rejuvenation is not happening. But there would be cases where with massive white dwarfs happening, the rejuvenation is happening, but we are not able to get through to them. But we will be looking for such objects with chemistry as well, so spectroscopy. So there's a plethora of compact objects discovered, subdwarf A, B, LM, etc. and they probably are formed through case A, case B mass transfer and similar class of objects, but we will go ahead in the next step and classify them and possibly predict what kind of a mass transfer mechanism is happening there. In the case of globule survey, we have this far UV optical plane is most sensitive to the helium abundance. And is there a connection between core collapse and binary protection? We are exploring it because NGC 362 has been an eye-opener because there are a lot of binary blue stragglers there and blue lurkers. We have to process more of study more of the core collapse systems. Omega Centauri does seem to have undergone some fraction of in situ enrichment, and it seems to have some very weird stars, and more data is required to understand what's happening there. And the extreme horizontal branch stars, which are actually very hot bare core stars in the helium burning, are better traced in far UVs, and we are able to cover some of the end evolutionary sequences, but more will come when we actually analyze the entire set of data and more clusters which are pending for analysis. I think I'll stop here, and this is my group, and many have completed PhDs and they've moved out, and yeah, thank you, and I'll take questions.
Thank you so much, Annapurni. It was a really amazing talk. Let me start taking questions from the chat first. We were having lots of questions during the talk. But in the meantime, if people have questions, please raise your hand or keep typing in the chat. So one of the questions we have is, does the collisions between two stars could generate strong magnetic fields that newly merged stars have more nuclear fuel to go massive and appear young, and they can still be a main sequence blue straggler star instead of evolving into a red giant? If it is right, any evidence there until now?
So when the two stars collide, they should obviously merge, but then the collision is not the total mass may not be conserved, depends on how exactly the collision happens. There are cases where, as I mentioned in the case where, sorry. The case where hierarchical triple systems are there, right? In this case. So there the merger happens where there would be some cases, but the point is that we think that some could be mergers, but unless and until we know they're not in binaries, I mean, we can think that many of them are collisional products like mini blue stragglers. And of course, that does not require, we don't have to invoke magnetic fields in this case as of, it's not mandatory to do it, but that will be a second order, a third order effect, but they will stay on the main sequence. Yeah, they will live to the extent that the core helium, the helium in the core falls under its own gravity to evolve. Yeah.
Okay, so another question we got is, what is the lowest possible mass for a white dwarf binary system? And can this be calculated, or is it just an observation-based number?
So in this case, like I mentioned, you can have a low mass and a high mass white dwarf, but the white dwarf for a single mass star evolution, it is 0.4. This is the observation. So you don't have anything going below it. But if you see them, they are stripped cores, and I don't know whether you can actually call them as white dwarfs. But right now we see at 0.18, but if the stripping has happened for some other reason, something smaller can happen, but which would mean that the mass transfer has happened within the main sequence itself. So you strip the core even before, like if you strip the core of leave the core of the sun and strip the entire envelope of the sun for some reason, what will be its mass? You might find it, but that's a possibility.
Okay. Another question we got is, how come the FUV and the NUV, not having much difference in wavelength values, have different kinds of mode for capture? That is, one is having photon counting mode and the other having integration mode.
How come FUV not having much difference in wavelength values? Far UV and near UV wavelength values are different. Like the far UV is 130 to 180 nanometer. In UV is 200 to 300 nanometer. There is a difference, and the way in which photons are captured is also same. Yeah, I don't know whether yeah, so it is, you can see it is basically 180 to 130 to 180, and this is, you can ignore this part, 200 to 300. It's
okay, so there is a
or
difference.
less, or I don't know, because that is how it is. The far UV mainly is between 100 to 300, 350 is the UV. And the U band comes in astronomy. Basically, ground-based U will start from 360 nanometers onwards. 380 maybe, because atmosphere absorbs most of it. You can't see anything below 380 from ground. Maybe 360 in high altitude. Beyond that, you have to go to beyond above the atmosphere. Yeah.
Okay, and also a note, if people have more questions, please feel free to raise your hand or type your question in the chat. I have one last question in the chat, which I'll read out. So what happened to a CAF2 WA filter? How is it different from CAF2 filter?
Yeah, okay. So these are actually as I mentioned, these are the names of the material which is used, but then they are renamed as the wavelength wise, which would make more sense. So the CF2 is basically 148, and the other is the standby filter. So there are, if you look at the filter wheels, there are, you saw a picture of filter wheel, right? So this filter wheel, you go in all the filters over here. So in one of them, this is the window mode operation, like the 148 is the one which has got a maximum wavelength coverage. It's got a standby thing, because if one goes bad, you will have another one. So there is a contingency in that. So all the filters are sitting in this filter wheel. You can see that, right? Yeah, filters are sitting here, but this is a contingency which both are calibrated, but we normally use the one and not the two. One has got slightly lower efficiency compared to the other.
I think
but both have the same wavelength coverage.
We just got another question. Urvashi, do you want to actually unmute yourself? And
I have read, yeah, okay, you can ask. Yeah, I'm reading it as well. Yeah.
Yeah.
So the question is, how are these different modes of observation decided, ma'am? What is the criteria or conditions? So the in UVAT, what happens is these are the filters. You also have GRISM, which I didn't mention. So you can also take image or spectrum. So like in these cases, if you want to put the GRISM instead of one day thing, you will get the spectrum. Okay, it's a slitless. So modes you can't change because it's a photon counting mode for UV. You can't change it into an integration mode, and visual also you can't change. But either imaging or spectroscopy you can decide. But other than that, you can't decide because that is already pre-configured. Let me put it this way. And what areas you can cover? If you look at the, I mean, I just want to mention that if you look at the galactic plane picture, used to be a big poster earlier on all wavelength, showing the galactic, how our galactic plane looks like, right? So X-ray, gamma ray, the infrared, near infrared, mid infrared, all that will come. UV will not come, because none of the observatories have been kind of, it's very, very bright. So you have a lot of stuffing regions, etc. Not been able to do. So here also the galactic plane is cannot be observed. And so above some B you can observe, galactic latitude you can observe. And also if it is pre-observed by Galax. So these criteria is already explained in the proposal submission form and etc. Based on that you can do, and proposals are accepted even from international people. So it's not that you need to be Indian. So there are partnership. You please check the AstroSat support cell for all the details. So proposal submission form, all the details and all that are available there.
Okay. Waiting to see if there are more questions. Maybe while people are thinking of other questions, I should try to wrap things up with a more kind of general question that I have for you. So, India had recently had many success in different space-based mission, right? Like we have AstroSat, We recently launched Aditya L1, and there were like lunar missions like Chandrayaan. So what are the next big missions that Indian space and astronomy community is thinking about? And related to that, are there priorities now to also expand on the ground-based observing facilities front and telescopes?
Yeah, so astronomy is a very expensive science because you need bigger telescopes either in the ground or in space for getting data. So in the case of ISRO, after the AstroSat, there was a call for proposals for future astronomy missions, for that matter. So we had submitted a proposal because in IAA, we have kind of gained expertise in creating space payloads and delivered 2 of them, right? Because one for nighttime and the other is for daytime solar as well. But then we know how to make space instruments. There are not too many institutions in the country who can actually do that. And so in that heritage has to be continued. So we had proposed for a 1 meter class telescope, which is in the UV optical range. And there is no UV sanctioned mission which can actually cover the UV sky and at good resolution. So what we had planned for was a 1 meter with a PSF of 0.2 arcsecond. You can actually resolve many of them. And also a small field like the WIPIC field, the HST field for multi-object spectroscopy, where you can, like the globular cluster centers or the nuclei of galaxies, etc. You can actually do 0.2 arcsecond resolution spectroscopy. So you can get the velocities, chemistry, etc. in the UV. So it's a unique thing, but we're still in the study phase. It's not moving forward as of now. There are also post-AstroSat, there's some Daksha mission, which is planned in the X-ray. That's also kind of, I don't know where it is. But there's a mission which is going to be launched now. It's an XPOSat. It's a polarization, X-ray polarization instrument that will go up now. There'll also be some more, I think, planetary missions coming up. But I do not know about the larger landscape. But in the ground base, we have Ares is established at 3.6 meters. That's the latest one. But IAA is planning to set up, Hanle is an interesting, or rather location where it's the promising area for a larger telescope. And our partnership with the 30-meter telescope has actually gained a lot of experience and expertise to handle larger projects and, bring larger telescopes. So we're proposing for a large optical telescope in the Himalayan region. And that proposal is getting ready. And Solar Physics Group actually wanted a bigger solar facility on the ground by the time Aditya is up, because you can look at the coronal mass ejections as well as the sun. Now you have to combine both, right? So you have to have a good resolution images from the sun.
Did she cut off?
Yeah, I think the video already froze a while.
We were about to wrap up anyway, so maybe we wait a few seconds to see if she comes back online.
Should we leave a message?
Yeah, and then we leave an email maybe.
If she's still there.
Okay. I think she cut off. So maybe also, I think we are way over time. So maybe we should wrap up and say thank you all for joining. And yeah. Oh, I think she's back.
I think some outage. Yeah.
Yeah, so we were about to say that thank you so much for your talk, Annapurni, and for all the questions, for patiently take all the questions from different levels and from different folks. So thank you so much. We are really happy to have you as an inaugural speaker. And we will continue with this colloquium series, as Prakriti and Sanskriti might have said in the beginning. We will invite each speaker in each month, so from different parts of the world, focus on India. So yeah, thank you so much. I think this was a great success, and thank you for help us kickstart this event. Thank you so much. And thank you all for coming today. Sorry, Prakriti, go ahead if you have any last words.
As Sanskriti said, we want to take a screenshot of the final window. So
sure, yeah, it'd be great if you can yeah,
Yeah,
start
thank
your
you
Yeah,
for
it's
video.
organizing this. I think I
comfortable.
look forward to listening to more talks. It'll be quite useful as well. Yeah.
Yeah, yeah.
So if you're comfortable, you can please turn on your video. I think some of the videos are still off. I'm just guessing. We can take a picture like this.
Give just like maybe 1 minute more to people.
Mhm. Should I take it now? Maybe we can just take it now. All right.
Thank you so much.
Done.
All right.
Right. Thank you everyone for coming.
Thank you,
We'll see you.
everyone.
Thank you,
Bye.
Annapurni. Bye.
Bye bye.
Thank you, Annapurni.
Thank you so much. Yeah. Bye.